Hello everyone, and welcome to the Implementation of Binary Search Trees lecture. This is going to be a two-part lecture. You can refer to the Jupyter Notebook for the code discussed in this lecture. We'll be jumping to the Jupyter Notebook from time to time to discuss larger chunks of code. You can also refer to the Wikipedia article on BST or binary search trees for more information on this subject. In this two-part lecture, we're going to be going over an overview of binary search trees and also an implementation of them in Python. Let's go ahead and get started. A binary search tree relies on the property that keys that are less than the parent are found in the left subtree, and keys that are greater than the parent are found in the right subtree. We're going to call this property BST property, the fact that keys that are less than that parent node are found in the left subtree, and keys that are greater than the parent node are found in the right subtree. So in an interview setting, when someone mentions BST or BST property, think of that specific property, that keys that are less than the parent go left, keys that are greater than the parent node go to the right subtree. As we implement the map interface as described above, that BST property is going to be our guide to implementation. So we'll see it crop up again and again. So here we have an example of a tree, and notice that the BST property here holds. So every node, and if you look to the left and right of the node, you have that BST property. All keys in the left subtree are less than the key in the root. All of the keys in the right subtree are greater than the key in the root. Notice that this BST property only refers to the direct parent, not the entire tree. So, just to reiterate this really important property, all of the keys in the left subtree are less than the key in the root. All of the keys in the right subtree are greater than the key in the root. So, now that you know what a binary search tree is, we will look at how a binary search tree is constructed. The search tree in the figure here, which is the last one I showed you, represents the nodes that exist after we have inserted the following keys in the order shown: 70, 31, 93, then the next level, 94, 14, 23, and 73. Since 70 was that first key inserted into the tree, it becomes the root. Next, 31, since it's less than 70, becomes the left child of 70. 93 is greater than 70, so it becomes the right child of 70. Now we have two levels of the tree filled, 70 level and then that 3193 level. So the next key is going to be the left or right child of either 31 or 93, which is where 14, 73, and 94 come into play. Since 94 is greater than 70 and 93, it becomes the right child of 93. Similarly, 14 is less than 70 and 31, so it becomes the left child of 31. 23 is also less than 31, so it must be in the left subtree of 31. However, it is greater than 14, so it becomes the right child of 14. So keep that in mind, and you can go back and reference these slides for that list ordering of the way the keys were inputted into this binary search tree. In order to implement the binary search tree, we will use the nodes and references approach similar to the one we used to implement the linked list and the expression tree. So go ahead and review that lecture on the nodes and references implementation in case you need to review it. However, because we must be able to create and work with a binary search tree that is empty, our implementation is actually going to use two classes. The first class we're going to call binary search tree, and the second class we will call tree node. You can begin to reference the Jupyter Notebook if you need to, but in this case, the binary search tree class has a reference to the tree node that is the root of the binary search tree. In most cases, the external methods defined in the outer class just simply check to see if the tree is empty. If there are nodes already in the tree, the request is just passed on to a private method defined in the binary search tree class that takes the root as a parameter. In the case where the tree is empty, or we want to delete the key at the root of the tree, we'll have to take a special action. And we'll discuss all of this in much more detail as we jump back and forth from the Jupyter Notebook. But the basics of the class we implement, called binary search tree, look like this. We have this init method, which takes in none and sets the root as none, and then also starts off the size as 0. So it's totally empty, has none as the root. Then we return length as just a method to return size. And also we use this special method __len, and it also returns size, but that allows you to use the len length built-in method in Python on your binary search tree. We also have this special method called iter, which allows you to iterate through the binary search tree, and we'll call that on root as well. Let's go ahead and jump to the notebook to check out the full tree node class and just go over some of the code. Okay, here we are at the binary search trees notebook. You'll notice we have the class tree node with some basic methods. There's quite a few of them, so that's why we didn't have them in the presentation. But it's the basic ones that we discussed earlier, such as hasLeftChild, isLeftChild, isRoot, isLeaf, and these methods just do exactly what they say. They check if it has a left child, they check if it has a root, or if something is a root, returns if it has any children, etc. And the binary search tree is just taking advantage of that tree node class as well, which is why we split it up. Go ahead and review the nodes and references implementation of a tree in case you want to refer to the tree node class here and get a little more background understanding on it. Throughout the rest of this two-part lecture, we're going to be focusing on some of these special methods such as putting items into our binary search tree, getting items, and then what's a little tricky is deleting items from a binary search tree and splicing them out, and this find successor method. Also, removing items from a binary search tree is a little complicated, and there's a couple of cases we need to consider there. So we'll be going over those in much more detail. But just as far as the basics of what the tree node class looks like, it just basically has left and right child methods and isRoot and isLeaf methods, which are essentially just checks or returns of self.rightChild or self.leftChild. So go ahead and review that in the notebook. But for right now, let's go ahead and go back to the presentation and discuss some specific methods used here. Okay. Now that we have that binary search tree shell and that tree node class, it's time to write the put method that will allow us to build our binary search tree. The put method is just a method of that binary search tree class. Again, you can refer to the Jupyter Notebook, but we'll also have screenshots of some of the code methods here. This put method will check to see if the tree already has a root. If there's not a root in place, then we just put the new tree node and install it as the root of the tree. If a root node is already in place, then put calls the private recursive helper function put to search the tree according to the following algorithm. So what it's going to do, it's going to start at the root of the tree, search the binary tree comparing the new key to the key in the current node. If the new key is less than the current node, we'll go to the left subtree. If the new key is greater than the current node, we search the right subtree. And that's due to that BST property that we were talking about earlier. When there is no left or right child to search, then we've actually found the position in the tree where the new node should be installed. To add a node to the tree, we create a new tree node object and insert the object at the point discovered in the previous step. So this is the code that does all that. Notice we have essentially two put methods, one with an underscore and one without the underscore. The one without the underscore is just for code factoring or refactoring reasons. So it looks a little nicer, and we use the underscore.put as a helper function to do that heavy lifting. So again, what's happening in this code is we start at the root of the tree, we search the binary tree comparing that new key to the key in the current node. If the new key is less than the current node, we search the left subtree. If the new key is greater than the current node, we search the right subtree. When there is no left or right child to search, we know we found the position in the tree where the new node should be installed. To add a new node to the tree, we just create a new tree node object, which you can see that happening here and here, depending where it goes. We also have the self.root equals tree node in case there's not a root already in place, which is essentially what the put with no underscore does by itself. It checks if there's a root. If there is, it calls that helper function. Otherwise, it just adds the tree node there. Note that this underscore put function is written recursively following the steps I just mentioned. Also notice that when a new child is inserted into the tree, the current node is passed to the tree as the parent. One important problem with our implementation of insert is that duplicate keys are actually not handled properly. As our tree is implemented, a duplicate key will create a new node with the same key value in the right subtree of the node having the original key. The result of this is that the node with that new key will never be found during a search. So a better way to handle the insertion of a duplicate key is for the value associated with that new key to replace the old value. For right now, we'll just ignore those duplicate subkey scenarios, but you can go ahead and explore and fix that code if you wanted to check for a duplicate key, and then replace the old value with it. And then here we just show a screenshot of that setItem method, which allows us to use the key value. And this is what inserting a node of key 19 would look like in a tree. So we go around, check which ones are filled, which ones aren't filled. So here at 29, we can see that 19 is less than 29, so it would be inserted into the left subtree. Once the tree is constructed, the next task is to implement the retrieval of a value for a given key. The get method is even easier than the put method because it simply searches the tree recursively until it gets to a non-matching leaf node or finds a matching key. When a matching key is found, the value stored in the payload of the node is returned. So this is the code for that get, and then it also has its own _get helper function. The search code for the _get method, the second one, uses the same logic for choosing the left or right child as that _put, that helper put method used. Notice that that _get method returns a tree node to the original first get method. And this allows the _get to be used as that flexible helper method for other binary search tree methods that may need to make use of other data from the tree node besides just the payload. And by implementing this special method, __getItem__, we can write a Python statement that looks just like we're accessing a dictionary. So that basically allows us to use the bracket notation that you use in a dictionary when you call a key from a dictionary. So that's why this is here. Using get, we can implement an operation by writing that __contains ___ method for the binary search tree. Again, this is a special method, and the contains method will simply call get and return true if it gets a return value or false if it returns none. So we'll have a couple special methods throughout the binary search tree. You can go ahead and check them out if you want more details from the Python documentation, but you can essentially just read the code and assume that they're allowing us to use built-in methods or syntax with Python for our specially created binary search tree class. So finally, we're going to turn our attention to the most challenging method in the binary search tree, and that's the deleting of a key and the removal of a key. This is what we're going to be discussing in part 2 of this lecture, but just to give you an idea of what we're going to do, that first task for deleting a node is to find the node to delete by searching the tree. And then if the tree has more than one node, we're going to use the _get method to find the tree node that needs to be removed. So in the next part of this 2-part lecture, we're going to be talking about deleting nodes and removing nodes. Okay, go ahead and review the Jupyter Notebook and the slides that we've gone over so far. So far we've gone over just get and put, and also just building out our basic binary search tree and using that tree node class representation. Okay, thanks everyone. I'll see you at the second part of this lecture, where we're going to go into deleting nodes from our binary search tree in more detail. As far as what you should have gotten out from this lecture, definitely that BST property, where keys that have a value less than the parent node go to the left, and keys that have a value greater than that parent node go to the right. That's really the key to remember binary search trees. All right, thanks everyone. I'll see you at the next lecture.